Today is lecture 7 in the course, and it's about gas and solids mixing. And I will start by showing the index for today for main topics. First is some basic concepts about mixing. Why is it important and how can we evaluate it? The second will be solids mixing, third is fuel mixing, and fourth is gas mixing. In a way, I was thinking that fuel mixing could be a sub-chapter or subsection of solids mixing, because fuel in fluidized bed boilers is often in a solid form. So is it in a way solids that are inside there? So it's strongly related to solids mixing too. Good. Let's start then with the basic mixing concepts. And first basic concept that we need to have with us is that of dispersion. And dispersion is described by a diffusion-like equation. This means that it's concentration gradients which drive the mixing, the transport. But what we have in a microscopic scale, that is diffusion, for example, of a gas species, and that happens through molecular collisions and so on. On a macroscopic scale, then we have dispersion. And why can they be described with the same equation? Well, because indeed the underlying phenomenon is that of a random walk. I will try to explain it a bit more. So, for example, here you have on the lateral direction how a particle or how solids will be mixing. If we start with a solids particle here, it will go up, and we focus on the lateral direction. The bubble will explode and it will have a distribution laterally, 50% to the left, 50 to the right. And then it will mix again, explode again, and it's again 50% to the left, 50% to the right, and so on. So in a way, it is a random walk in which you have a length of this free path, the mean free path, which is this distance, and also you have a characteristic time, so the residence time of these cycles, so to say, and that is very much alike. It's a direct analogy to what you have in the microscopic scale with diffusion. You have the length of mean free paths, and also you have some characteristic time between molecular collisions. So in the end, you have a completely other scale. Here we are talking decimeters or even meters, and we are talking seconds. So it's much longer spatial scales and time scales, but still the phenomenon is the same, that in the lateral direction here we would have a random walk. And that is why we can describe dispersion through a diffusion-like equation then. Again, the scales are completely different. One is microscopic, the other one is macroscopic. But it's an important concept to have with us. It's dispersion. And dispersion is created here, as you see, by convection. These are convective flow patterns. But since they are repeated and they are stochastic, so they have the same, there is they have the same probabilities to go on each side, then it becomes like a random walk. So it's the sum of stochastic convection, so to say, but also there is, of course, some diffusion, but diffusion is completely neglectable in front of this macro scale. So very much like diffusion for the microscopic scale, we can use the Einstein equation to calculate this coefficient governing this mixing. It's a diffusion coefficient for gas diffusion, for example, or fluid diffusion. But now we are speaking dispersion, so we will call it dispersion coefficient. But indeed, the equation is the same. So you have here a certain characteristic time between these cycles or between these events, and you have a characteristic length. At the microscopic scale, again, it's the mean free path. But here at the macroscopic scale is the size of these structures, which are repeated. As I warned yesterday, I'm starting to lose my voice. Good, then the Einstein equation tells us that the coefficient, diffusion for microscopic scale, dispersion for macroscopic scale, reads something like this. It goes with the square of this characteristic length divided by the characteristic time. And units are, as you know, for diffusion coefficients, square meters per second. And this is very useful because if you have data, for example, if you know how a particle is moving at this macroscopic scale, and you have enough good statistics, so you can simply calculate, okay, how much has been over a certain time, how much has this particle displaced. If you have enough data points, you can calculate the dispersion coefficient, and with enough good statistics, enough good data points, you can then estimate a dispersion coefficient. So this is a useful equation, and you can develop it a bit more. You know that the length divided by time, that is velocity. So if you want to estimate some kind of characteristic velocity for this kind of dispersive mixing, it would read something like this. So velocity would grow with the dispersion coefficient, but is also dependent on size. And this is very interesting, because what this means is that if you throw in here some solids and you want to calculate what is the characteristic velocity for these solids to reach this point, for example, at the middle of the bed, that will be given by this equation, and d will be a certain d for all these cycles. So that is given, divided by this length. Okay, then you have a certain number for this characteristic velocity. But if you want to calculate the characteristic velocity for the whole bed here, what happens then? Delta L, the characteristic distance, this length here, is increasing, and this means then that the velocity, the characteristic velocity for this mixing has decreased. This means that solids will have a certain velocity, mean velocity, to reach half of the bed, and that velocity will be much higher, double as high, than the one for reaching the other end of the bed. And this is a very known phenomenon for dispersive mixing. Dispersive mixing is relatively fast in small geometries, but it gets slower and slower as we grow up in size, in scale. So for very large scales, dispersive mixing starts to become slower, and that has to do with the nature, so to say, of random walk. Okay, so this is one first basic concept that we will use today, that of the dispersion coefficient and of the dispersive mixing. One example that we have here is that if we inject gas from the side here, if we typically inject it here from the side wall, the gas plume will look more or less something like this. And it's not a straight line here at the boundary, so to say, but it's a curve. And this is a direct consequence of what we see here. For short distances here in the beginning, the velocity is relatively high. So you have a quite large gradient with zeta, with height here. But then as the gas has to reach farther penetration, so delta L is increasing, then the effective velocity is going down. So the rate at which this gas penetrates to the opposite wall decreases with height as time goes, so to say. And the explanation to this, what we see here, is given by the nature of dispersive mixing. Good. So the typically how we describe the mixing of a certain phase, whether it's a gas phase or a solids phase, is by transport equations, in which we have then a convective term here, and this is the second term on the left-hand side. So this is convection of some species. And the other mixing term is the first on the right-hand side, which is the dispersive term. So now we are speaking macroscopic scale, and this D is not the diffusion, but it is dispersion at this macroscopic scale. So the whole balance for these equations is a mass balance. You have the gas phase in the first equation, you have the solids phases in the second equation, but you see they are completely analogous. The only thing we are changing is the sub-indices, gas versus solids. And we have, as typical in a mass balance, the cumulative term. This is the transient term. It disappears if we are calculating steady states. And what we have is the two mixing terms, as I already mentioned, the convective one, which goes with velocity. So this is the mixing by velocity, how the flow is transporting a certain species. And the dispersive mixing that I just introduced then. And this is in a way a convective mixing, as I said, or a combination of convection and diffusion, but where convection is dominant. So the whole thing, we call it dispersion then. And finally, we have in a mass balance, the chemical term or the source term, if any reactions, dissipation, generation of the balanced species exists. So the same goes for gas and solids, and we have two mixing terms, two transport terms. Again, they are the convective ones characterized by velocity or governed by velocity, and we have the dispersive ones characterized by these dispersion coefficients. Today we will look much at these dispersion coefficients. What do we know about them for the solids and for the gases in fluidized beds? And when it comes to the velocities, the typical assumptions is that, well, you know what is your volumetric flow of gas that you are injecting, you know the mass flow and you know temperature. So you should be able to calculate what is your gas velocity here in the furnace. The typical assumption it is that it is a flat profile, so you have a certain gas velocity that you can calculate at each height here in the furnace. And it's given by, of course, this expression. And when it comes to the solids, typically one rough approximation is that the solid's vertical velocity or also horizontal velocity by pure convection, so to say, is 0 here in the bottom region. So everything is governed by dispersion. While here in the more dilute region, where solids are dragged up by the gas, they have an axial vertical velocity upwards, which is given by the difference between the gas velocity and their terminal particle velocity. So this is a summary of what is roughly the convective terms in these balances. And we will, as I said today, focus on these dispersive terms, how they look like. Notice that if we can approximate these velocities through these expressions, and we can give values to these dispersive coefficients, then the system is determined. Then you can go and solve your mass fractions here, and that will give you the concentrations of gas and solids then. So before we move on, the Peclet number, that's a dimensionless number, which is comparing then the weight of these two terms. How important is convection in front of, sorry, in front of dispersion? So it's the ratio of the two. Convection is characterized by a velocity, of course, and dispersion needs to be characterized by some kind of velocity too, and that's the dispersion coefficient divided by L, and this is in line with what we saw in the former slide here. You see D divided by L. That gives you a characteristic velocity for the dispersive mixing. So with the Peclet number, you can easily say which of the two will be governing if you can neglect even some of the two, for example. And before we start looking at the mixing of different phases, one last concept very much want to introduce for you, I think it's very important, is that of the Dam color number. It's again a dimensionless number. And it compares the kinetics and the transport. And why is it useful? I will try to illustrate it with this example. So in a fluidized bed, we would feed fuel from the side wall. This is the fuel port. So the combustible, the fuel, will be injected from a certain location. It's a punctual injection. While our oxidizer is homogeneously fed, spread through the whole cross section. And this tells us about the challenge then. We want all this fuel to meet all this oxygen. And that may be relatively easy for small units, of course. But if you imagine that these are several meters, 5, 6, 7, even 8 meters, then we start having a challenge here, because the fuel will fall here. It will start oxidizing, and maybe it has converted before it reaches the other end of the unit. This is not a desired situation, because then here we would have a lack of oxygen. We would have no oxygen here, because it has all been consumed by this fuel. While here we would have a lot of oxygen, which is not meeting any fuel at all. And this is an undesired situation. So we need here to compare how fast this fuel is able to mix here laterally compared to its reaction rate. So if the fuel is mixing very fast, then that would be a desired situation. We would make sure that it is well spread and the oxygen is also well spread, and then we have a good situation. If the fuel is mixing slowly, then we have the problem I just mentioned. Is it enough then to evaluate the fuel mixing only? No, the fuel mixing has to be compared to the kinetics. So how fast enough is fast, so to say? Well, it depends on how the fuel converts. If we have two different fuels, one converting very fast with fast kinetics and the other one converting slow and mixing at the same rate, of course, the one that is converting slowly will have a more beneficial situation, because it will mix, it will convert slowly, so it will have time to spread here and meet the oxygen on the other end. The fuel which has fast kinetics will be more problematic, because it will stop converting after some time and the mixing will not be, or there won't be enough time for the mixing to spread the whole fuel. So the Dam color number compares these two. Here we have a situation in which we are feeding, this is the cross-sectional concentration of fuel, and we are feeding fuel from this location. So if we have a slow mixing or very fast kinetics of this fuel, or a combination of both, we would reach such a situation within an imbalance of the fuel concentration. If we have very fast mixing or a fuel with slow kinetics, we would reach this situation, which is much more typically much more desirable. It doesn't create any maldistribution of the fuel. To compare this, we have the Dam color number, as I said, and it is expressed as the ratio of the kinetic and the transport rates. The transport or the rates are the inverse of time, so 1 divided by second typically. So if you want to calculate a transport rate, you would need to take a characteristic velocity for that transport and divide it by a certain characteristic length. In this case, this velocity would be, if you have a convective mixing, would be the velocity of that flow. If you have a dispersive mixing, I have shown in the slide before how you calculate a velocity for dispersive mixing. And then you need to divide it by this length, of course. Okay, then you have this dimensionless number, and this dimensionless number tells you what situation you have. If it's a low number, then you have good distribution over your cross section. If it's a high number, then you will have a maldistribution. And if it's around 1, then you will have some intermediate case, of course. I have expressed this in terms of a rate ratio, but you can express it as a ratio of characteristic times. But then you need, of course, to inverse the two. So the transport ends up here, and the kinetics end up in the denominator instead. So this was introduction. I will just end up by exemplifying a bit more how we apply this in practice. And we can do this with some modeling that we have done. And this is modeling of biomass combustion in this case, but it would apply to coal, peat, waste, any other fuel. The basic principle is that for any solid fuel, you have mainly 3 fields that will be converted, so to say, in the fuel, and that is moisture, volatile matter, and the char. And the moisture is released very fast, so the kinetics are very fast. So I've tried to illustrate this by this bar. The volatile's release is relatively fast, but not as far as moisture. And finally, you have the char combustion or the char conversion, and this is much slower in terms of kinetics than the moisture or volatile release. So we have a low bar here. The mixing rate of the fuel we will assume it to be more or less the same for the three. Of course, the particles as they convert, as they release moisture, volatiles, as they convert its char, they will change their properties and the mixing rate can change somewhat, but as a rough assumption, we can assume them to be constant. So which combinations do we have? We have some mixing rate, which is constant, but we have the kinetics for each one of these processes that differ strongly. What do we have then in the case of moisture? Well, a moisture release will look like this. It happens very fast, so it will, most of the moisture, we will find it close to the fuel filling port. And if we calculate the damp color number, it will give us a high damp color number. If we go for the opposite extreme case, that's the char conversion, it has very slow kinetics. And given the same mixing rate, then we will have a low damp color number. This means that combustion will typically be relatively well spread over the whole cross section, at least of this unit that we are modeling here. Of course, if the unit grows in size, the damp color number accounts for that also with a characteristic length, and maybe we don't have such a good situation as the one modeled here. And the case in between is that of volatiles and intermediate kinetic rate, more or less in range with the mixing rate. And then we have some intermediate case, which is not as that heterogeneous as moisture release and not that homogeneous as char combustion. So this is an example on how to use the damp color number. It's a number that you can calculate on the back on the envelope in 1 minute, so to say, if you have the numbers, and it gives you a good idea or a good picture of how your distribution or your mal distribution can look like. Good, these were 3 basic concepts then, dispersion, including the Peclet number, and then we had the damp color number also. And now we move on to the second section here today, and that will be solids mixing. So first of all, instead of just feeding you with material and data and literature points, data points from literature, I would like to first make a short reflection. What is the role of these things? Why is the mixing of bulk solids important? Why caring at all? Well, in first place, it can be because they are active materials and they need to be active parts in different reactions, heterogeneous reactions. Typically in fluidized bed, it's the fuel that is the solid that has to react, that has to be the main responsible for heterogeneous reactions. But sometimes the bulk solids, the fine material, is also reacting, is also active. We have, for example, for coal combustion, we have sorbents which take care of the sulfur capture, and that needs, these are typically carbonates that need to then to capture, well, sulfate, sorry, calcium sulfate, calcium oxide that needs to capture SOx, sulfur emissions, and turn into a calcium sulfate. You can have catalysts, for example. You can have oxygen carriers in order to improve your oxygen distribution and so on. More and more, we are seeing improvements, new technologies within fluidized bed combustion that use active bulk solids. So this is becoming a relevant field within fluidized bed combustion, the use of active bulk solids. So one first important thing why caring is because we see more and more that we use them for being or for driving heterogeneous reactions. A second one is the thermal mixing. Here I will introduce the concept of an effective thermal conductivity of the bed. So if we would have a bed here and we would heat up this point, and this happens, for example, by combustion, when we have combustion of the volatile matter, of the gases, for example, or of the char, coal, when we have a hot spot somewhere in the unit, there will be a an effective spreading, diffusional, dispersive spreading of that heat, so to say. And there is an analogy, we can describe this as a thermal conductivity of the bed. Well, this thermal conductivity of the bed consists of three terms. One is the thermal conductivity of the gas and solids, which are there, as if the bed was fully static. That heat would spread through the gas and the solids. And then we have two terms related to the mixing. Of course, if we have gas or solids which are in the hot spot and mix to some other place, they will carry that heat to other locations. That is a convective transport, but it can be in dispersive mixing, it can be described as a dispersive, as a thermal conductivity. So we have these three terms, and the point here is that if you make very fast numbers, you will see that the first two terms are the first and the third term will be completely neglectable in front of the mid term, which is that of the solids. So the solids will be the ones telling us how good is the thermal conductivity in our unit. If we have a lot of solids mixing, if our solids were mixing extremely fast here, we would see the same temperature all over the place. We would have an infinite thermal conductivity. So that's an important thing. It is governing how the temperature field looks like. Then we have an effect of thermal flywheel also. And this means that our solids, they act as a sensible energy buffer, even chemical, if the solids are active. And this stabilizes temperature. I want to illustrate this with a very simple example. So imagine this tube reactor. We have hydrogen here, and at some point we mix it with oxygen at a hot temperature. If we measure temperature along the tube, it would look like this. Then we would have combustion. At this point, temperature would rise, and we would have this exothermic combustion process that would rise the temperature of this flow. Well, this is no mysteries. You can calculate the numbers for this adiabatic temperature and so on. But what happens if we have solids in the picture? Inert solids, I'm not saying active, just inert solids. If we have sand here, which is not reacting with this oxygen or this hydrogen, we just, together with the hydrogen flow, we put a lot of sand with it. This hydrogen is carrying sand particles. What happens then to the temperature profile? Well, this happens. These particles need also to be heated up by this heat released. The heat released here by the reaction, by the combustion, is the same, but now it goes to not only heating up the gas flow, but also heating up the particles. And that is a lot of mass compared to that of the gas. And that means that there will be still a temperature increase, but it will be very, very small, much smaller than in the absence of particles. And this is called the thermal flywheel effect. You give the whole system a heat capacity through this mass of solids, which is much larger than the mass of gas. And this heat capacity provides a thermal flywheel. And this means that in fluidized bed reactors, you will have relatively constant homogeneous temperature fields because of this, because of the presence of solids. And finally, the solids, they govern the heat transfer to the walls. And what is meant here is that in the end, what we want here is to have combustion, but we want to be able to extract that released heat somehow. And what the solids do is that if you have combustion here inside, you have an upwards flow of solids, they gain this heat by this phenomenon of thermal flywheel. They gain the heat that is released, the solids heat up, they store this energy, and when they get in touch, in contact with the side walls, which are tube walls, water walls, then they will transport, or they will give this heat to the walls. They will cool down and provide this enormous amount of heat that they have stored to the walls. So the solids, indeed, what they do is that they catch up, they buffer up the heat released by combustion here, and whenever they get in contact, in touch with the heat extracting surfaces, then they release this heat. They are, in a way, heat extraction agents. So bulk solids are important in many different senses. Now that I hopefully have convinced you about the importance of the bulk solids, we can look at how the mixing looks like. You may recognize this picture from a former lecture. These are the mechanisms for this solids mixing. Again, dragged up by bubbles, and because of a mass balance, if the solids get dragged up here, they need to come down somewhere, and they do that here. And you can identify several of these so-called mixing cells besides each other, aligned besides each other, so to say. So this is in the bottom region, and then as we discussed earlier, also if you have a lot of these mixing cells aligned over a cross section, then you can describe this as a dispersive mixing of the solids. So typically we would, what you will find in literature if you look for solids mixing are dispersion coefficients. And the background to that is that the solids mixing follows this pattern in the lateral, in the radial, horizontal direction. Good, then we'll look here at what the literature says, and here is a very nice review from Broad. And what we see is that this lateral dispersive coefficient, it increases with the Reynolds number. This means with velocity. And we have different works in literature. And what you see is a logarithmic y scale, and this is telling us about how little we don't know and how complex the phenomena is. So for a certain Reynolds number, you have a spread of even up to 2 orders of magnitude. And this tells us about the complexity. But it illustrates somehow that at least what we know is that dispersion coefficient increases with velocity. And this is the lateral direction. Another thing which is widely accepted now is that the lateral dispersion of solids is much slower than the vertical one. So if we throw solids here, the dispersion in this direction will be much slower than the one in this direction. So they will mix in this direction much faster, at a faster rate than in the horizontal direction. In addition to that, we have that the horizontal direction is typically much longer than the vertical extent of the bed, so to say. And that adds then to this difference in rates. So that makes lateral mixing typically much more challenging, or much more limiting than the vertical one. Typically, vertical mixing in the bottom region is typically counted to be perfect because of the high rate and because of the low height of the bed. Instead, in the lateral direction is the opposite. We have a slow rate and we have a relatively long length for this mixing. So what we have here for the axial direction, again, about 1, and this is much larger than the ones that we see for lateral mixing. Good, we go on with the fuel mixing. And first I would like to again, feed back to what I was saying in the beginning with the Damköhler number. Here we have at the Chalmers boiler 2 concentrations of CO. So CO is a result from volatile release and also from char conversion. And here we have one case with 100% coal and one case with 50% coal, 50% wood. Otherwise, the rest is the same. The bulk solids are the same, the fluidization velocity is the same, the bed height is the same, the geometry, the unit is the same, temperature is the same. So what do we see here? If we are feeding from this location, why do we see this maldistribution when we are combusting biomass? And why it looks more convenient, more well distributed when we are combusting coal? Well, there can be 2 reasons for it, and it relates again to the Damköhler number. Biomass converts faster, is more reactive. The char in biomass is more reactive, but mainly also biomass, the content of biomass is mainly volatile matter rather than char. And volatile matter, as we saw before, it releases very fast. So this means that the kinetics for biomass will be much faster. This means that given the same mixing, if it mixed equally fast as coal, it would have stopped converting at a certain length, at a certain penetration, much shorter than the one for coal because of this difference in kinetics. That can be one aspect, and is for sure one aspect. The other aspect is that biomass particles typically are much larger than coal particles, and thus the mixing, the lateral mixing of this fuel is slower, and this also affects then the transport rate. So we will have faster kinetics, faster K kinetics. We have slower K transport. The combination of both leads to this situation then. And this is 50% boot. If we would have 100% boot, this would be even more exaggerated. So this is one of the main challenges in burning not only wood, but also waste, low-rank fuels, fuels which are characterized by a high volatile content. Then most of the energy is released very fast in the volatilization stage. And this fast release, this fast kinetics, they represent a challenge, especially in large boilers. We don't have time enough to spread this fuel before it has released most of its energy. Well, having given some background of why this is important, we can look again at the numbers out in literature. Here we have a work by Niclason, 2003. And what we see is a combination of different fluidization velocities and different reactor sizes here. So this is background for the data. And these data lead to these dispersion coefficients. And what we see is that apparently the dispersive lateral horizontal dispersive coefficient increases with velocity and also with the bed height. So taller beds give us a better mixing of the fuel. But again, as you see, for a given quantity, for a given velocity and bed height, again, we have a huge spread in the y-axis in the measured values, so about 2 orders of magnitude. And again, that tells us about the challenge and how much it is still unknown in this. So there are much more parameters playing a role here than just velocity and the bed of the height. And this is something that we are intensively working with, and I would claim we are starting to find some explanations and models that can describe this spread, which other variables play a role here. Good. This is another work by Sette and others, and what he showed also is that looking at data from literature, that there was an effect of the cross-sectional area of the bed. So not only bed height and not only the velocity, but how large the unit is. So here we see that the larger the unit in which experiments were made, the higher the dispersion coefficient. So dispersion seems to have also this effect of unit size. And again, we see large variations for a given size, a given unit, still large variations in the lateral dispersion coefficient, but a clear trend of increasing the dispersion coefficient with the unit size. Here we see from it's 3 orders of magnitude in difference. And finally, what we get is that the largest units, so to say, we are in the scale here of some square meters, reach lateral dispersion coefficients of about 0.1 here. This is for the lateral direction of the fuel, and it can be described through these dispersive patterns, and we have seen why here before. They follow this same pattern as for the bulk solids, and it's a random walk on a macroscopic scale. So then it is dispersive. But what happens with fuel at in the other direction, in the vertical direction? Is it dispersive? Well, the reason is not, because dispersive or diffusional nature of a mixing means that if you would wait for steady state, then everything would be well distributed. There wouldn't be any concentration gradients in steady state. But we know from experiments that particles or fuel particles in a fluidized bed, they tend not to distribute themselves homogeneously in the vertical direction. So we cannot use dispersion to describe fuel or the mixing of fuel in the vertical direction. I will try to explain a bit more on this. So what we have here is that fuel particles would be or would experience forces. Of course, there is the gravitational force downwards. There is a buoyancy upwards. So light fuel will tend to be flotsam and be not being immersed in the bed. But then there is also a drag from the bed material, or all these fine solids will drag the fuel in different directions and so on. So it's a number of forces that act on these fuel particles, and that will tell us whether the fuel will be well spread through the bed, or it will be flotsam, or it will be jetsam. Sometimes it's just immersed in the bed the whole time and it never comes to the surface. We did some experiments with 3D tracking of fuel particles. It's a technique that we have developed here. And what we see here, the line is giving us the bed height at minimum fluidization. So here we have the vertical distributions of fuel, of different fuels. So the bed height in fluidization is somewhere here. So the dashed line is at fixed state, packed bed at repose, so to say. And then when it fluidizes, it expands. So we are somewhere here then. And what we see is that for very flotsam fuel, if we take biochar, so the char that we have after biomass has been dried and devolatilized, it's a very light char, about 200 kilos per cubic meter, that will mainly float on the surface. It will be here. Then if we have biomass, fresh biomass, it is heavier because it contains all the volatiles, all the moisture, and it will still very much be on the surface, but we see that almost half of the surface below this curve is inside the bed. So it will be 50-50 distributed between the bed surface or above the bed surface and inside the bed. If when we did experiments with an even heavier particle, then it penetrated the more, it immersed the bed even more. So the mixing here will depend on the physical properties of this fuel. The heavier it is, the more it will tend to immerse the bed. Also size will play a role and so on. So these are things that we have been studying. But what I wanted to come here is that we increase velocity. What we see then is that for the same particles, the same bed properties, when we increase velocity, then we see that there is this increase in velocity helps then this flotsam particle to start penetrating the bed also. So this particle is not anymore just floating on the bed surface, but it starts to penetrate the bed. And this is important because if you have, for example, catalytic agents, or if this is a cold particle and you want to make sulfur capture, then you would have the sorbent is inside the bed. If you have your cold particle floating here and releasing all the sulfur up, then the sulfur will never meet the sorbent, and you will have a hard time capturing this SOx, the sulfur oxide emissions. But if you manage to have your cold particle immersed at least part of the time, then this sulfur oxides will meet the calcium oxide and be captured by it. So approaching then the gas mixing, and here I would like to again recall the concepts of diffusion and stochastic convection. So if we inject a tracer gas here at some location, and we have a gas stream, a gas flow going up, what we will see from this tracer gas is that after a certain height, it will have a certain distribution like this. If you compare this distribution to the diffusion coefficient of the gas, the microscopic diffusion, it will not be in agreement. The microscopic diffusion should give here a much smaller, much more narrow distribution. But what we see from experiments is a wider distribution. So it cannot be explained only by diffusion. It has to be explained by, again, stochastic convection. So what happens for a gas? We will have fluctuations in the lateral direction of the convective flow, and these fluctuations are stochastic. They can be described in a relatively random way, random distribution, so to say. But it's called stochastic convection. And then what we see here is a sum up of the two effects. On the macroscopic scale, what we see is mainly stochastic convection, but it's true that while this plume here of gas is in this case going to the left, it also has diffusion inside it, so to say. So what we see is the contribution of both. When you have hundreds of these plumes together, then they will sum up to this distribution that we measure up here with time. Well, then the result of the both is what we called, again, dispersion. And typically, convective term, the stochastic convection, will be dominant in front of diffusion. You just make the numbers and see if you compare the dispersion coefficients to the diffusion coefficients, you will see that these dispersion coefficients are much larger. Good. Then this is what we get. Then a distribution of this local injection, and from this, then you have, of course, the time, because you know the velocity of this gas flow, and you know the spread, so this characteristic length, and from this you can calculate dispersion coefficients with the expressions I gave you in the beginning of this lecture. And this is done in literature, and this leads to these data points then. And as we see here, this is the dispersive mixing coefficient for lateral mixing of the gas divided by the viscosity. And here we have the Reynolds number. So it's a velocity in a way, and also size of these different units. What we see here is, again, some variation up to 1 order of magnitude. So again, we have this uncertainty here. There are other aspects playing a role. But the main trend is telling us that when we increase velocity or when we increase the size of the unit, we get, again, larger dispersive mixing coefficients. Interestingly enough is that if you take the expression for turbulent single phase flow, so without any solids, how the gas would disperse, would mix by turbulent diffusion, so to say, then you would get this solid line here, which agrees very nicely with the dispersive coefficients for solids. So this is a very interesting observation then, that a good approximation of this dispersive solids coefficient, gas coefficient, sorry, with a multi-phase flow in the presence of solids can be given by single phase expressions. Sorry. So what does this mean then? And also that we see a line here. Well, if we see a line here, it means that we can express it like this. The y-axis is proportional to the x-axis. And if we manipulate this expression a bit more, we will see that the ratio of the velocity of the gas divided by the characteristic velocity of the dispersive mixing, this is a certain length, or the dispersive coefficient divided by a certain length here. You have this Peclet number in the beginning of this lecture also. So this expression tells us that Peclet is constant. When you have a constant Peclet number, then you obtain a line in this plot. So this is one main finding from experiments, data points, gathering data points from literature. More data from literature when it comes to gas mixing. Again, the review by Brolt is a reference work here. And he plotted here against gas velocity what are the different radial gas dispersion coefficients. And you see again a large spread, and part of this spread can be due again, or can be partially explained by the unit size. As you see here, unit size is present in the x-axis. And again, larger units seem to reach larger dispersion coefficients. Yes, and what we have in the axial direction, so there is also mixing in the axial direction, again, is somewhat higher values. Is similar to what we see in the solids, that in the axial direction we have somewhat higher values than in the lateral direction. But again, for the same velocity, the spread is enormous, or is not, to me, is a bit unsettling, so to say. One would like to be able to explain this better, this spread. Well, here I have provided you for solids, fuel, and gas in both directions, information, values, references for how to calculate the mixing. But I would like to end up with a remark, and unfortunately, the remark is that life is not always as easy as it seems. And here I have an explanation, or sorry, an example for this. This illustrates much the nature, the fluctuating nature of the flow, the gas solids flow inside circulating fluidized beds. And this will help us understand the complexity of it all. If we simply model gas mixing with a transport equation, with dispersion coefficients, and with dispersive and convective coefficients, then we might risk not to have the correct results. Why? Well, because there is, again, this fluctuating aspect that we need to account somehow. I will try to illustrate it by this. These are measurements in the Chalmers boiler. So we have gas concentration on the y-axis along height at the center line of this boiler. So what we see here is that in some locations here, we have presence of both oxygen and methane. And we have temperatures which are about 850 Celsius. If you go to literature and take the kinetic rate for methane combustion at this temperature with oxygen, then you would realize that in theory, if you have these concentrations at this point, there shouldn't be much methane left at this location a bit farther up with this residence time and so on. But there is. Methane seems indeed to be more or less in the same level as oxygen. It seems like it's not combusting at all, almost. So what happens? What is the explanation to this? Well, the explanation is relatively complex, but interesting, I would say. There is no coexistence. You don't find oxygen and methane at the same place, in the same place at the same time. So these are measurements in the same place, but the explanation is that these are averages of fluctuations. So this is a time average of a fluctuation for methane and a time average of a fluctuation for oxygen, and they are there at different times. So in the same place, yes, but not in the same time. You will see with your probes either methane or oxygen, but hardly both at the same time, because if they are there in the same place at the same time, they will react and convert to something else. And this is very clearly seen in these measurements. These are zirconia cell measurements, and these probes, what they do is that they give a signal which tells you about the presence of oxygen, so to say. So when the output is low, it means that you have oxidizing conditions, you have presence of oxygen. When the output is a high voltage, then you have no presence of oxygen. If we look here at the bottom, this is at a very low location, a half a meter above the bottom grid, then you would see these that you have mostly absence of oxygen. Sometimes oxygen appears here locally very fast. This is second scale, so this is very fast. These are maybe 1 second or fractions of a second, I would say. And what are these valleys here, very sudden valleys here? Well, these are bubbles exploding, or these jets that are bypassing through the bed that we were mentioning in the beginning of this course. If you remember, sometimes the jet would open the whole bed, create a shortcut for the gas, and then the air takes the chance. The air sees suddenly a low pressure path to take, and it takes it, of course, because we have low pressure drop distributors. Then the air takes that path, and this is what you see here. Here the bed has opened, the air has seen the chance, and you can measure it. So then you have these fluctuations. Sometimes you will see these ghost bubbles, they are called, but these gas structures which are very rich in oxygen, which is air that has managed to bypass the bed. And these structures survive all the way up. Of course, the more we go up here in our furnace, the signals will develop. And here, for example, you have a mixture between reducing and oxidizing conditions. And finally, here we have at the top 8 meters, so it's somewhere here in this location, how the signal looks like. So they look differently because we inject secondary air and so on. But what I wanted to strengthen with this figures rather than the how the signal develops is that at any location you would have strong fluctuations between reducing and oxidizing conditions. And of course, when you average this gives you a certain average time average methane concentration, oxygen concentration, and both will be non-zero, but this doesn't mean that they're both there at the same place. How do you model this? Well, if you do CFD, then those are transient simulations and you should be able to model that. But if you do an easier modeling with only transport degradation, with only mass balances, which are not necessarily transient ones, then what you need to do is to modify your reaction rate for the homogeneous reactions to account for these fluctuating effects. If you have the reaction rate as the kinetic rate found in the books, then you will never have oxygen and methane at the same place. Instead, if you want to force that, you need to account and for fluctuations and limit your reaction rate based on this effect then. And that was it for today, for this lecture on mixing. I've tried to introduce some concepts, dispersive mixing, what it is, what do we mean by it, how it does relate to convection and to diffusion. It's mainly stochastic convection. Also the Peclet number, the Damköhler number, what do they tell us about the mixing? And then given some explanation, literature data and explanation to them for the solid mixing, fuel mixing, and gas mixing in both directions, both the direction of the flow, the axial vertical direction, but also in the radial horizontal direction, which is typically the critical one in this kind of boilers. So I thank you for your attention, and I will be